Since humanity first looked skyward, we have dreamed of taking to the air, skirting the laws of physics and pushing engineering science to ever greater heights. The power of flight ranks among humanity's greatest achievements. In this episode, we journey from the experimental breakthrough of the Wright Brothers to the contemporary icon of commercial travel that is the Boeing 747. And from today's cutting edge of experimental flight, the LightningStrike, to tomorrow's vision of interplanetary travel in SpaceX. This is the story of air power. Invisible, but far from intangible, air is the name given to the Earth's atmosphere. Itself a source of power, both devastating and helpful. Air provides resistance to travel. Each time we take to the sky, we are working with air and against it. October 25, 2007. This was the first commercial flight of the largest passenger plane in the world, the Airbus A380.
It's no different to any other aeroplane, whether tiny, medium-sized, large or huge. The aerodynamic principles are exactly the same. But of course it's rather more interesting watching something that big fly.
Nicknamed Super Jumbo, this enormous craft measures 73 metres long, with a tail fin standing at the same height as a 10-storey building. Such is the scale of this craft that 530 kilometres of wiring runs it. Weighing a massive 580 tonnes, the A380's paint job alone tips the scales at around 650 kilograms. With a plane this huge, one question looms large. Just how does it get airborne?
To achieve that, you need a very aerodynamically efficient aircraft. So you need very large, very efficient engines combined with very aerodynamic design and very efficient and very large wings to generate the lift to keep the aircraft in the air.
Powered by 4 turbofan engines, the unique aspect of the A380's flight is the aerodynamic design of its wings. A design that began as a compromise. The optimal wingspan is 90 metres, well outside airport restrictions.
So had they built it with a straight wing, it would have become too large for basically all the airports in the world. So it would not have been allowed to start or land anywhere just because of its size.
Scaling its wings back to 80 metres, the A380 added unique wingtip fences to maintain an extended aspect ratio without extending length. These distinctive wing fences also serve to reduce the potential hazard of this huge and hugely powerful craft.
When you have an aircraft, the flow around the wing creates something that is known as the wingtip vortex. So the bigger the wing, the bigger these vortices.
An aeroplane's wing generates lift by creating pressure changes in the air. As the wing passes through the air, air moves quickly over the top and slower underneath, resulting in the upward force of lift. A byproduct of this is wake turbulence. With the high and low pressure air left swirling behind the wing to effectively form a horizontal tornado.
These vortices present two primary problems. One, the most important, is that they significantly degrade the efficiency of the wing, its ability to generate lift without generating drag. The other is that they actually present a safety issue for aircraft following behind.
The extended wing fences of the A380 serve to distribute the wake turbulence and drive it upward rather than down. Not a bad result for a wing design that started out as a compromise. with little else by way of compromise, to understand how so many of us can so easily and so comfortably take to the sky, we must look back to more humble beginnings. A little over 100 years ago, in this inauspicious North Carolina field, a truly auspicious event in aviation occurred. It was here, in December 1903, piloting a craft of wood, fabric and wire, that Orville and Wilbur Wright became aeronautical legends. Covering a distance less than the wingspan of a modern 747, this was the first time in history that a powered, heavier-than-air aircraft achieved sustained flight. While the Wright brothers were not the first to pilot experimental aircraft, their fundamental breakthrough was in controlling that flight. It was the Wright brothers' work selling and repairing bicycles which convinced them that a flying machine could be steered and balanced with practice. With the right controls, the Wright brothers believed that learning to fly was like learning to ride a bike. So while their contemporary aviation research focused on building more powerful engines, the Wright brothers worked on steering. And it was the invention of their 3-axis control system which was the game changer. This ingenious design, which today remains standard in all fixed-wing aircraft, allows the pilot to steer and maintain equilibrium.
The fixed-wing design was very successful, and from that point onwards, fixed-wing aircraft became the dominant form of aviation.
By the early years of the 20th century, powered flight had become an established technology. The potential of aeronautics for combat, sport, exploration or travel was increasingly recognised around the world, and a period of rapid development was ushered in. A period where the true power was in human bravery. Perhaps no one better exemplifies the pioneering spirit of aviation's golden age than this man, Charles Lindbergh. Known as Lucky Lindy, this former US airmail pilot shot from obscurity to world fame in the course of a single flight. Piloting a purpose-built monoplane, the Spirit of St. Louis, Lindbergh's 5,800-kilometre journey from New York to Paris was simultaneously the first solo transatlantic flight and the first non-stop flight from North America to mainland Europe. Short on funds but high on self-belief, Lindbergh piloted his single-engine craft for a grueling 33.5 hours. Battling storms and navigating by the stars to land in Paris as a hero on May 21, 1927.
Everyone wanted to meet this daring young man. Even as he posed for these films with members of France's distinguished Aero Club, the entire world was clamoring for its brand new hero.
A feat of both human and mechanical endurance, the achievement brought new public interest to aviation, sparking what was known as the Lindbergh boom. A period in which airmail volume increased by 50% and pilot license applications tripled. For all the bravery and sacrifice of aviation's golden age, the limits of the piston engines that powered these flights were well known.
So after the Second World War, we really saw the rise of the gas turbine, the jet engine as a technology.
Invented years earlier by Frank Whittle for the Royal Air Force in 1921, the jet engine works by firing gas backward in order to thrust aircraft forward. A breakthrough almost as revolutionary as the Wright brothers' first flight.
The attraction of the gas turbine is that you could get even more power out of a given size and a given weight.
Breathing in air through a gas-fired turbine, the jet engine compresses this air through a series of high-speed rotor blades. Forced into a combustion chamber, the compressed air is then sprayed with fuel and ignited. With the expanded gases forced out through the propelling nozzle at the back, the aircraft is thrust forward at high speed. Though still in its infancy, by the end of the Second World War, the turbojet represented the next great leap in aviation. During the war, high-altitude, high-speed bombers were in high demand, leading the English Electric Company to develop designs for just such a plane, the Canberra.
The Canberra is a high-altitude light bomber with great striking power and a speed believed to be over 600.
Featuring an elegant, streamlined design, the Canberra is more notable for the fact that it was the Royal Air Force's first bomber to utilise the power of the newly developed turbojet engine. Coming into service after the war in 1951, the Canberra set a new world record as it flew from Northern Ireland to Canada, becoming the first jet aircraft to make a non-stop transatlantic flight.
As for the trip, that smashed all records as we know. 4 hours, 40 minutes from Aldergrove to Gander, Newfoundland.
Throughout the 50s, Canberras flew higher not only than other bombers, but than any other aircraft at the time, repeatedly setting world altitude records. The highest a Canberra flew was in its third record-breaking flight, reaching 21,430 metres in 1957. The power of the turbojet combined with its clean design made the Canberra a remarkably versatile aircraft, filling a variety of roles from tactical bombing to photo reconnaissance. Although retired from more than 50 years of military service, Canberras remain in the air today, performing meteorological research and ground mapping work. With peaceful skies, the established power of the turbojet and a surplus of heavy bomber airframes ready for conversion to passenger transport, the end of the Second World War also marked a turning point for civil aviation.
Probably the most rapid period of development in aerospace, certainly in aviation, was that following the Second World War.
One of the first to forge ahead in this new and exciting space was the Vickers Viscount. Employing the gas turbine engine to power propeller blades, the Viscount brought the turboprop aeroplane to the public. But it was the de Havilland Comet that truly burst onto the scene, claiming the glory of being the world's first jet airliner. Manufactured in the United Kingdom, the Comet featured a sleek modern design with 4 turbojet engines buried in the wings, large square windows and a pressured cabin, allowing for comfortable and efficient flying at high altitude. But these commercial pioneers were doomed by a fatal design flaw. If passengers are to breathe while flying at high altitude, a plane's cabin must be pressurized against the low air pressure outside. Increasing cabin pressure while ascending and decreasing it while descending places the structure of the plane under tremendous stress as it expands and contracts with each takeoff and landing. This is what led to the Comet's downfall. A series of tragic and highly publicized accidents saw several of the planes burst apart in mid-flight, resulting in dozens of deaths.
This is the tragic scene of the Comet disaster near Calcutta. Wreckage of the aircraft smashed almost beyond recognition.
After extensive testing, a structural weakness was finally identified around the Comet's square window frames. Suffering metal fatigue after repeated pressurization cycles, the Comets effectively became ticking time bombs, unable to contain cabin pressure at altitude. Despite undergoing a period of extensive redesign, which saw the craft rebuilt with oval windows and reinforced structures, the airline's reputation never recovered. But the quest to conquer commercial airspace did not end, and heeding the lessons from the Comet's design failing, rival manufacturers developed new and improved airliners in quick succession. In the 60s, Douglas Aircraft was the more established manufacturer. and its DC-8, the first commercial transport of any kind to break the sound barrier, took a commanding share of the market. One plane went on to change all that. With its wide body and distinctively humped upper deck, this is one of the most recognizable planes in the air. It is the original jumbo jet, the Boeing 747.
Well, that was a name that was conjured up by the popular press, not by Boeing. There's still people in Boeing who don't like it being called the jumbo jet. It rolls off the tongue, doesn't it? Jumbo equals big, jet, and it's stuck.
Entering service in 1970, the 747 surpassed the DC-8 to take control of the commercial air market by offering vast improvements in performance and comfort.
It revolutionised airline travel, there is no doubt about that. It was able to carry 2.5 times as many passengers as the Boeing 707 and the Douglas DC-8, which were the standard international airliners of the time, which meant that the seat mile costs were lower.
The engine technology was moving from what we call low bypass turbofan technology to this brand new idea of high bypass turbofan technology, which is really the basis of all modern transport engines.
With air entering the turbojet through a fan, the bypass ratio is the amount of air that bypasses around the engine versus the air directed to the engine's core for combustion. All air passing through the initial fan has increased velocity, allowing turbojets to take some thrust from the core and some from the fan. So while combat aircraft use a low bypass ratio, burning more fuel for maximum power, commercial jet engines make use of a high bypass ratio for increased fuel efficiency.
Air travel was still the domain of the richer part of society. But as aircraft size grew, what that meant was that you could bring the cost for the individual traveller down.
There's millions of people who could not previously afford to fly internationally suddenly could. And that was the revolutionary part of the 747. It brought in the current era of mass air travel.
Thanks to the advances in civil aviation, this is what modern air travel looks like today. Often taken for granted, it is the ground-level infrastructure that has enabled the omnipresent reach of air travel. But for all the advances in air power, the forces of nature can still bring us back to Earth. Volcanic eruptions are some of the most awesome natural forces on the planet. Firing clouds of ash high into the air, these particles can enter and potentially stall aircraft engines, creating no-fly zones spanning tens of thousands of square kilometres.
The single biggest improvement in aviation safety was the move from piston engines to gas turbines, because gas turbines are inherently more reliable. The problem is they're designed to ingest air. They're not really designed to ingest particles.
Volcanic ash clouds may be a rare inconvenience for planes, but for helicopters, the risks posed by dust particles are faced every time they take off or land on sandy surfaces. Beyond limiting visibility, sand stirred up by helicopter rotor blades is breathed in by the air intake of the engine.
So while it's not necessarily the belief that a single flight through the dust will result in catastrophic failure of the engine, we're certainly extremely worried that multiple flights will degrade the performance of those engines.
With helicopter engines running at high speeds and high temperatures, once inside, sand particles are sped up and superheated. Captured at 4,000 frames per second, this footage shows the high-speed sand particles slamming against and melting onto the internal engine hardware. The result is an underperforming, unreliable engine deteriorating at approximately 10 times the normal rate, a real risk to the lives of those on board. The solution may look something like this. Currently experimenting with the durable, heat-resistant properties of ceramics, military scientists are hopeful of developing an engine coating that can withstand the ravages of sand. Finding the right chemistry is a process of elimination, but initial results are encouraging, powering helicopters, indeed all aircraft, to operate in an even wider range of conditions. Of course, it wasn't so long ago that the challenge was operating a helicopter under any kind of conditions at all. Unveiled in Nazi Germany in 1936, this is the craft that proved the viability of the helicopter, the Focke-Wulf Fw-61. While not the first to achieve rotary flight, the Fw-61 easily outperformed contemporary rivals to establish itself as the first truly practical helicopter, providing the basic design that future helicopters went on to develop. Bearing the name of its principal designer, Professor Heinrich Focke, the Focke-Wulf took the fuselage of a light aircraft and replaced the wings with steel outriggers in order to mount three-bladed rotors on either side. These large rotors spun in opposite directions, providing stability. And while the forward propellers on the engine gave the Fw-61 the look of an autogyro, their shortened blades did not provide power for forward flight, instead cooling the 160 horsepower engine. And this is where Focke's chief innovation lies. Taking the gas turbine engine that revolutionized aeroplanes, Focke converted it so that instead of producing jet thrust, the engine powered a spinning shaft which in turn spun the rotors. This is turbo-shaft propulsion, and it is the system still used by the majority of helicopters today. So impressed was the Nazi government with the Fw-61 that it became part of their propaganda campaign during the war. Placing Germany's famed female pilot Hannah Reitsch at the helm, the helicopter was flown for nightly shows in front of large crowds. Such indoor displays could easily have ended in disaster, but thanks to the Fw-61's robust control system, Reitsch, with less than 3 hours practice, successfully flew the craft night after night without incident. Following the war, the most significant advances in helicopter technology took place not in Europe, but in the United States. And there is one man who deservedly takes much of the credit for this, Igor Sikorsky. Born in Russia, Sikorsky was already an established aircraft engineer and pilot when he migrated to the US in 1919. Founding the Sikorsky Aircraft Corporation, he established himself in America as a leading innovator in aviation. And it was this craft, first flown in 1940, which cemented his reputation, the Vought Sikorsky VS-300. Here, the famed innovation concerns a long-standing, or rather long-spinning problem with helicopters, how to stop them spiraling out of control.
And of course, the big problem is that if I have a rotor spinning in the air, then I need to stop the aircraft spinning in the opposite direction.
Newton's third law states that every force has an equal and opposite reaction. And in spinning rotor blades to fly, a helicopter's body tends to spin in the opposite direction. This spinning force, called torque, must be counteracted in order to achieve stability in the air.
And then we need to use things like tail rotors or have more than one rotor to provide that anti-torque to stop the aircraft spinning. And that adds extra weight, complexity, and more points of failure. So these problems have hounded aeronautical engineers for many decades.
Enter the VS-300. With just a single set of lifting rotor blades and a single main gearbox, anti-torque is achieved through a vertical tail rotor. Power is traded off here, with the tail rotor counteracting the main lifting rotors in the name of stability. But the simplicity of its design made the VS-300 worth the compromise. And it's hard to argue with success, with the tail rotor blade configuration pioneered by the VS-300 still seen on most helicopters today. And Of the helicopters today, there is one that casts a long shadow over all others. The Boeing AH-64 Apache. Heavily armed and heavily armoured, the Apache has been compared to a flying tank. Equipped with radar jammer, bulletproof glass, sophisticated sensor equipment, laser-guided targeting, chain guns, and the aptly named Hellfire missiles, the Apache is tricky to detect, difficult to damage, and near impossible to hide from. And to its targets, utterly devastating. But here is where the flying tank comparison falls short. The Apache is also incredibly agile. Modifying the tail rotor blade configuration pioneered by Igor Sikorsky, the Apache employs dual tail rotors, each with 2 blades. More than providing anti-torque force, this setup in combination with a digital stabilization system is optimized to provide remarkable maneuverability, a handy trick when evading enemy fire. A deadly combination of strength, firepower, and agility, the Apache has ruled the skies since it began service in the 1980s, with over 1 million combat flight hours to prove it. But today, a new breed of combat helicopter is rising. This is the Sikorsky S-97 Raider, a compound helicopter designed to provide the one thing conventional helicopters lack: speed.
The limitation of most helicopters is they can't fly very fast, because as the aircraft flies faster and faster, one of those blades is going so slow that the air over it stalls and it no longer produces lift.
On the battlefield, speed is power. And the Raider is built to get into the fight fast and get out even faster. It does this in 2 ways. The first is a coaxial design, essentially stacking 2 counter-spinning rotors on top of each other to eliminate torque without diverting power from their lift and thrust capabilities. Eliminating the need for a stabilizing tail rotor, the Raider is free to bring in its second addition, a pusher propeller out the back to provide even more forward thrust.
There's always been this problem of trying to go faster in a helicopter. We reach a speed of about 200 knots, we can't fly any faster. So these compound helicopters use wings or extra propulsion systems to put less load on the rotor, and by doing that they can actually get faster.
The Raider offers more than pure speed. It aims to revolutionize all aspects of helicopter performance with increased range, altitude, and payload performance. From assault missions to search and rescue, the Raider is customizable to suit a variety of roles as the next generation of military helicopter. With varying degrees of sophistication, helicopters of all sorts have long boasted a particular advantage over planes: the ability to take off and land without a runway. This inevitably raised the question, could a plane do the same thing? Needing a runway is a particular problem for combat aircraft. Air bases represent large, valuable infrastructure, difficult to protect from enemy attack. The need for fighter jets that could operate from improvised bases close to enemy lines was clear, and this was the solution. The Harrier, better known by its informal name, the Jump Jet. Continuing development throughout its lifetime, the first jump jet emerged in the 1960s as a rare success story in the quest for vertical takeoff and landing capabilities. So how did the jump jet succeed where so many others failed?
They had 2 pairs of nozzles, and so in combination, The Harrier could generate thrust at different angles to either short takeoff, manoeuvring in the air, or vertical landing.
Once airborne, the nozzles revolve to push the plane forward. Simple in theory, difficult in practice. Such maneuvers demand tremendous skill on the part of the pilot and tremendous power on the part of the plane. Capable of hovering for just 90 seconds, in this time the plane uses over 500 litres of water to cool the engine. Vertical takeoff is not possible when the plane carries its full loaded weight, so in most cases, a short takeoff is employed. Shortening the runway, ramps are often used to allow the plane to jump into the air, hence the name. In addition to the limitations of their vertical takeoff, jump jets were only capable of subsonic flight.
By going to that large high bypass engine, you are restricting the ability to make the aircraft aerodynamically efficient for supersonic flight.
Nonetheless, the Harrier Jump Jet was for many years the only plane capable of vertical takeoff and proved its worth in combat.
There was a desire to develop a follow-on to the Harrier that could have all the attributes of the Harrier of short takeoff and vertical landing, but also be able to fly supersonically. We now see a successful solution, and that successful solution is the F-35 Lightning II, developed by Lockheed Martin.
Today, while the Jump Jet has retired from active service, its legacy remains as the first aircraft to successfully combine the best aspects of helicopters with planes. At DARPA, the Defense Advanced Research Projects Agency, the search continues for the ultimate aircraft that can do it all. And DARPA is not afraid to think outside the box. This unconventional creation may represent the future of vertical lifting technology. Named LightningStrike, the unmanned craft has entered into experimental testing. With a hybrid electric system powering its array of 24 thrusters, the LightningStrike is seeking to set a new benchmark, taking off and hovering efficiently and going faster than any rotorcraft before it. The power of flight takes many forms, and in the 1960s, an ancient technology was reinvented, taking us to new speeds and new heights. It was this technology, 700 years after it was first discovered, that ultimately launched us into the space age. The rocket. Dating back to at least 13th century China, rockets operate on the simple principle of action and reaction. With the majority of their weight consisting of fuel, rockets burn this fuel in order to expel high-speed exhaust, thrusting them in the opposite direction. Simple, but effective. Long used in fireworks and artillery, it was the introduction of liquid fuel instead of gunpowder that brought rocketry into aviation. Compared with air-breathing engines, rockets offer a lightweight source of tremendous power. And it was rocket power that took us faster and further than ever before. This is what the marriage between rocket and plane looks like. The North American X-15. Operated by NASA and the US Air Force from the late 50s to the early 60s, the X-15 was the most successful of the X-planes. A series of experimental aircraft built to test new aviation technologies.
It's essentially a rocket that flew only for about 2 minutes every time, so it had just only fuel enough for that.
And so the X-15 had two primary missions. One of them was to fly as fast as it could through the atmosphere, and that was to look at thermal structural design. The other was to fly as high as it could to the very edge of the atmosphere where you could no longer use traditional control systems.
Almost half a century since it was last in the air, the X-15 remains the fastest manned plane ever flown. With an unofficial top speed of 7,274 kilometers per hour.
That could go up to more than 6 times the speed of sound, so Mach 6. And that holds the record of the fastest atmospheric vehicle that was ever built and flown.
Just how did the X-15 power such astonishing speeds? With this, the XLR-99 rocket engine. This was the world's first large rocket engine capable of increasing and decreasing its power, as well as stalling and restarting. The XLR-99 also provided a frightening amount of power, burning a propellant mixture of oxygen and ammonia to produce a staggering 250 kilotons of force.
It was really a multi-stage system because it was not able by itself to take off from a runway. Instead, it was hung under the wing of a B-52 bomber. And so that B-52 bomber became the first stage. And so that carried it to altitude, and that meant that it already had a head start when it was launched. And then once clear of the B-52, it would light its rocket engines. So it had onboard fuel that it would burn for a very short period, but that was enough to accelerate it all the way up to Mach 6.7. So that's almost 7 times the speed of sound, which is 3 or 4 times faster than a fighter jet, a supersonic fighter jet.
The test flights of the X-15 made history, not only setting a speed record that remains unbroken today, but an altitude record that went unrivaled for 40 years. Of course, the goal of these flights was about more than setting records. It was about research. Over the 199 flights the X-15 undertook, data was collected across all areas of aviation, testing everything from heat shielding and hypersonic flight to the physiological stress on pilots. Considered the most successful flight research program in history, the data gained through the X-15 proved invaluable for the next great frontier of aviation. The quest to fly beyond the atmosphere of the Earth into outer space is a dream as old as humanity. This dream came to a head in the space race of the 1960s.
It was actually the Cold War and the effort to beat the Soviet Union into space and the government funding and the defense backing that really resulted in all the achievements in space.
The Soviets took the lead early, launching the world's first satellite in 1957, and 4 years later, successfully placing cosmonaut Yuri Gagarin into orbit, making him the first man in outer space. But the ultimate objective remained, as outlined by President Kennedy.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
This ambitious goal was tasked to NASA's Apollo program, which began in 1961. And 8 years later, on Apollo's 11th mission, it was 2 men, Neil Armstrong and Buzz Aldrin, who achieved that goal. And what powered the Apollo 11 on its voyage to the moon? Rockets. Really big ones. The Saturn V was the rocket that shot the Apollo 11 into history. Almost 40 years later, it remains the tallest, heaviest, and most powerful rocket ever built. Operating on a 3-stage system, the first and most dangerous stage was simply getting this giant into the air. Packed with 770,000 litres of kerosene and over 1 million litres of liquid oxygen for combustion, the first stage rocket ignites and, with thrust confirmed, is released from the launch tower.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Burning for 2.5 minutes and carrying the vessel to an altitude of over 60 kilometres, the first stage shuts down and separates, falling back to Earth, where it will be burnt up by the atmosphere. Switching to a mixture of liquid hydrogen and oxygen, the second stage rocket propels the spacecraft into the Earth's orbit before being jettisoned. Expelling exhaust to transfer momentum, once in the vacuum of space, rockets are able to work at maximum efficiency, and it is from here that the Saturn V's remaining rocket engine propels the craft towards the moon, with the lunar module making history by touching down on the surface of the moon. Getting to the moon is one thing, getting back safely is another, with the most dangerous part of any space mission being re-entry into Earth's atmosphere.
Anything that comes from outer space typically travels with tremendous speeds, speeds of several kilometers per second.
Traveling through the vacuum of space, there is nothing to slow movement down. But when fast-moving objects, like meteors or Apollo command modules, encounter an atmosphere, the atmospheric gases in front of them are compressed extremely rapidly, causing them to heat up.
They have a several kilometers per second speed by the time they get into the atmosphere. If they were to crash with that speed onto the surface, that would be a major explosion and certainly very unpleasant for all involved.
The Apollo command module has a blunt body design, intended to create high drag and push against as much air as possible.
You have to slow down, and the best way to do this is to convert the kinetic energy, the speed, into heat. And you do this by generating a massive shockwave, because that's exactly what a shockwave does. A shockwave slows the flow down and converts the kinetic energy into temperature.
The shockwave around the Apollo module kept the flaming atmospheric gases from coming into direct contact with the vehicle. Nonetheless, the command module got hot, with its surface reaching temperatures of over 2,700 degrees. Coated with an ablative heat shield designed to melt away, it appeared from below that the command module had caught fire, when in fact it was functioning perfectly. With the shield eroding away from the vehicle, it diverted heat, keeping the history-making occupants safe for their eventual splashdown into the Pacific Ocean. Spurring the desire for further research and exploration of space, the Apollo missions highlighted the need for a more sustainable spacecraft, one that could make multiple trips to and from space. This was NASA's solution.
The Space Shuttle system, an amazing vehicle, probably one of the most amazing machines ever built, one of the most complex machines ever built. One of its prime aims was to bring the cost of space access down.
These were the vehicles that helped build the International Space Station and conduct cutting-edge space research. They remain the only manned space vehicles to have made multiple flights into orbit.
The Space Shuttle partially achieved reusability. So the orbiter is the only part that goes into orbit and then comes back. There were also some more traditional, large, solid-fueled booster rockets strapped to the side of the stack. Once they had expended all of their solid fuel, they would be released from the stack as it continued towards orbit, and they would fall back towards the Atlantic Ocean. The shuttle continued towards orbit, still attached to its external tank, and so when that tank was empty, when it had expended that fuel, that tank would be released and that would fall back through the atmosphere. And so it would actually burn up during its descent. And so that was not recovered.
Once in orbit, the shuttles provided the crew with everything they needed to live and work in space. And as with the Apollo program, returning to Earth was the most dangerous part of the mission.
The crews that flew the space shuttle were coming through the atmosphere at about 23 to 24 times the speed of sound during their initial re-entry. They were entering 7 to 8 kilometers per second. And so we would probably say that to date, that's the fastest manned winged aircraft.
The angle of re-entry is crucial, with the slightest error causing the craft to break up or skip off the Earth's atmosphere like a stone over a pond. After gaining re-entry, the challenges continue. Now without power, the shuttle must rely on pure aerodynamics to land. Generating lift with its small, swept-back wings, the shuttle slows its descent in a series of S-shaped banking turns before gliding onto the runway for touchdown. The Space Shuttle program was not without tragedy, but the desire for space exploration has not abated. With unmanned satellite and probe technology continuing as a safe and reliable means of space research, the challenge for these crafts is in harnessing an efficient form of power in the vacuum of space. This is the answer: the plasma thruster.
So if you've got a satellite in orbit and it's got a mission life of 2 years, 5 years, 10 years, you need the fuel that you put in that satellite at launch to last that long. Now, with chemical thrusters, you would not be able to make it last that long, but with a plasma thruster, you can because it's highly efficient.
We're using plasma to generate thrust on a spacecraft. And we do that by converting electrical energy, which you can store very efficiently on a spacecraft, into kinetic energy.
While they may look like the stuff of science fiction, plasma thrusters are actually an incredibly simple and well-established form of propulsion in space. One with the promise of powering space exploration into the future.
Once you're in space and there's no friction and there's no gravity to counteract your movement, you can use these plasma thrusters, which are incredibly efficient, to go to Mars, go outside of the solar system, anything you want to do.
Today, the space race remains as competitive as it ever was. The only difference is that the race is no longer between countries, but companies.
When I was a kid, I read a lot of science fiction, and a lot of the science fiction that had been written envisaged that it would be, the American dream was that private companies, rich individuals, would actually lead the journey into space. Because, that's how America saw itself, as the home of the entrepreneur. Fortunately, in parallel to this thinking, of course, was that we had a number of very successful, very rich individuals who had grown up with the dream of spaceflight that had been inspired by what NASA had done.
With shared goals of commercializing space travel and even colonizing other planets, 3 companies have emerged as leaders in the modern space race. Under founder Richard Branson, Virgin Galactic is seeking to become the space line for Earth. Blue Origin, set up by Amazon founder Jeff Bezos, has even loftier ambitions, with Bezos describing his ultimate goal as having millions of people living and working in space. Also working on big rockets, SpaceX is seeking to reduce the cost of space travel and harbours hopes of colonizing Mars. Such goals could be dismissed as science fiction, but with billionaire tech entrepreneur Elon Musk as CEO, SpaceX is already breaking records and setting new standards for space transport. Through experiments with reusable launch system technology, SpaceX has refined propulsive landings to the point where in 2017, it became the first to successfully relaunch and land the first stage of an orbital rocket. In their race to revolutionize space technology, these companies have set their sights on more than that. This is the forefront of aviation's next great leap. Daring to dream big, the corporate space race is drawing on the funds of its eccentric billionaire backers, but also on the power of the human spirit and its drive to explore and discover new worlds. From the first powered flight to the first lunar landing, the astonishing and rapid progression of aeronautic science has changed the world many times over. Proof that with the power of mastering the air, not even the sky is the limit.